Welcome to The Explainer. Today, we're digging into the hidden world of minerals, and I mean that literally. They're the building blocks for just about everything, from the salt on your fries to the smartphone in your hand.
All right, let's kick things off with a bit of a riddle. What do a diamond, your everyday table salt, and the iron holding up a skyscraper all have in common? They're all minerals. And that simple answer is actually the key to understanding, well, pretty much everything about how our planet works and how we've built our modern world right on top of it.
So that brings us to the big question. What is a mineral, really? The official definition is way stricter than you'd probably guess. The simplest way to think about it is this. Minerals are basically the building blocks of rocks. Yeah, they're like nature's Legos. One little piece can be part of a pebble, or you can stack a whole bunch together and build an entire mountain range. But here's the thing, not just any old brick gets to be called a mineral. So what does it take to get into this exclusive club? Well, geologists have this super strict 5-point checklist, and you gotta tick every single box to qualify.
And here's that list. Okay, the first three are pretty straightforward. It's got to be solid, it's got to be naturally occurring, so not man-made, and it has to be inorganic, meaning not from a living thing. But the last two? Those are the real deal breakers. You have to have a fixed chemical formula and a specific repeating atomic structure. It's that perfect internal pattern, that crystal lattice, that gives a mineral its unique properties. You miss even one of these five, and sorry, you're not a mineral, you're just, well, a rock.
All right, so once something passes the test and gets its official mineral card, what's next? Well, we classify it. Geologists start by splitting them into two huge families, and it all comes down to one simple question. Does it have metal in it? And those two families are, you guessed it, metallic and non-metallic. It's pretty self-explanatory, right? Metallic minerals are where we get our metals. Think iron, copper, gold. Non-metallics, on the other hand, give us everything else. Stuff like salt, quartz, and yeah, even diamonds. And what's really cool is that where you find these minerals tells you a story about the Earth's past. Metallic minerals? They're often born in really intense situations, forged in fire and pressure. We're talking ancient volcanoes or the incredible forces that smash continents together to build mountains. Non-metallics, though, they can pop up in all sorts of different and often much calmer environments. But okay, how do you tell one mineral from another when you're out in the field? Well, geologists basically become detectives. They look for a set of unique physical clues that act like a mineral's own personal fingerprint. They're looking at all these different properties. Things like its streak, that's the color of powder it leaves when you scrape it, or its luster, which is just a fancy word for how it shines. And here's the kicker. All of these clues, every single one, points back to that one crucial thing we talked about earlier. That perfect, repeating atomic structure on the inside. That internal pattern literally dictates everything you see on the outside. Now, probably the most famous test of all is for hardness, and it's such a simple but brilliant idea. Can this mineral scratch that one? To figure this out, geologists use a really straightforward scale that's been the gold standard for like over 200 years. And here it is. Mohs scale of hardness. It just ranks 10 common minerals from the softest to the hardest. The rule is simple. Anything on the scale can scratch anything with a lower number. So a diamond, sitting pretty at a perfect 10, can scratch literally everything below it. And then you have talc, all the way down at number 1. It's so soft you can actually scratch it with your fingernail. Crazy, right? Okay, for our last section, let's zoom out and connect all this to the real world. Why does any of this matter? Well, it turns out these specific substances are absolutely critical to, well, our entire modern technological society. So we know what minerals are, we know how to tell them apart, but to actually use them, we gotta find them first, right? That's where the idea of a mineral reserve comes in. It's just a known source of a mineral that we could mine but haven't yet. And trust me, where these reserves are located on the planet has a huge impact on global economics and technology. Just look at this world map. This shows us where the world's most critical minerals are being produced. And it reveals something pretty startling. The resources that literally power our modern lives, I'm talking everything from our phones to green energy, are packed into just a tiny handful of countries. Let's zoom in on a specific example. See the Democratic Republic of Congo there? They produce a mineral called cobalt, and their share of global production is, well, it's this number, 70%.
Let that sink in. 70% of all the cobalt on the planet, the stuff that's absolutely essential for the batteries in your phone, in your laptop, in electric cars, it all comes from that one single country.
Okay, now shift your eyes over to China, and let's talk about a mineral called gallium. If you thought 70% was a lot, brace yourself. The number here is just staggering. 96%.
That's right, almost all of the world's gallium, and mineral that is absolutely vital for making things like high-speed computer chips and advanced electronics, is produced in China. This is a perfect example of how the geology of our planet directly creates the geopolitics of our technology.
So the big takeaway here is pretty clear, right? The stuff we use every single day is totally connected to this global map. The lithium in your phone battery, the palladium in your car that cleans up the exhaust, the rhenium that allows a jet engine to not melt, all of it starts as a mineral, in the ground, in these very specific spots around the world.
And that leaves us with one final and really important question to think about. As our technology gets more and more advanced and more hungry for these special materials, who's going to control the minerals that build our future? The answer to that, well, it's probably going to define the next 100 years.